And we should all be here.
And I have some stuff to hand back. There. Okay, I want to just, when I call your name, please come up and you can grab your second part of your quiz. The other thing, a couple people emailed me after I emailed the quiz out. When I mark the quiz on Google Sheets, I press a button, I get a spreadsheet of all your answers. Then I can check that your answers weren't mismarked wrong. I correct those, put it in my mark book. So I believe my mark book has your correct mark, but when I said release it to the students, when I change it on the sheet, I don't think it now changes on your actual Google form. So I'm gonna go back and double check that. And then I'll change it right on the Google form, so I think that will give you an update, or you can at least check on the assignment on the Google Classroom and see what it does. And if you don't see a change, come and see me. I'm doing this afternoon, so I should be done by later on today. And do that. If there isn't any change and you think there should be, just come and see me. Okay, when I call your name, please come up. Jimmy, Alejandra, Naomi, Hugo. Ben, Lisa, Zachary. William, Felix, Jonathan. Nope. Zoe. Zahir. Zane. Ariel. Kieran and William K. I don't think you took it. I don't think you took it. You were here with it. Yeah. You will get it. It's just omitted because it was a small quiz on it, and then it just pops to the next quiz. You've now done another quiz. Larger quizzes are tests you have to make up. Small ones that are going to be retested that are mostly just formative, not so much. Okay. I will, although actually we should probably come up with a couple more examples. I believe we had lots of examples here for our chemical change. Those of you who were here on the Friday, you did a reaction where you saw some chemical changes and the signs. Our physical change needs to be updated. Our examples, erosion. What was smack? Because now I'm thinking drugs. There we go. Other examples of physical change. Yeah.
State like water.
State like water. So a change in state. Liquid going to solid. Solid going to liquid, melting, boiling, all that sort of thing. Yep. Zane?
Kieran and I don't have one of these. You're on it,
Oh. Check the back folder area. It looks like the wooden box at the back corner. It's often where and look underneath piles. It looks like the cleaning staff took them all off the desk, so. It looks like this on the front page. No, it looks like that on the front page. It says reactions on top. Anyway, your example. What is it? Ahem. Zane. Ooh, good question. Does anybody know enough about batteries to make a guess as where a charging battery would go? Yeah. The reason it would be chemical is what you have here. Charging battery. I'll do one of the simplest ones I know, which is the old-fashioned lead battery. So lead battery will have Pb solid, and it can go to Pb plus 2 electrons. And there are your electrons that come out that then you use for energy. But if you pump energy into it, you can get that. And then the battery builds back up again. So there's actually a chemical process going back and forth. Lead battery will go bad because inside of this, to make sure the electrons can move around, there's sulfuric acid. And you can get precipitate, and once that's built up and locked on, it can't go back and forth anymore. Now, I don't think you've ever seen reactions like this before. We deliberately put the electrons in. Most of the time you see something like this, you'll see something like, let's go with Pb plus HCl goes to PbCl2 plus H2. Oh, not H2O, there's no oxygen in that. That type of reaction, this is normal Pb solid, and this, because of the 2 there, is Pb plus 2. It has actually changed what it is. It has gotten rid of 2 electrons. This chlorine is secretly -1, and here it's -1. This hydrogen is secretly +1, and here it's 0. Just like that lead was 0. So it's gone back to its natural state. So electrons have jumped from one to the other. We usually show it to like this. You won't see it in this form until you hit grade 12. They're called half reactions because we're only showing about half of what's going on. This will give me a good opportunity to address one of the things in the quiz. Everybody did their Bohr model, I think, really well. The one thing, because zoom tight, I probably should review, there's just a few, atom versus ion. So when I ask for a Bohr model of the atom, there is no charge. Whereas an ion has a charge. So if I ask for, say, lithium, then it's 3 protons, 6, 7, 4 neutrons, 2 electrons, 1 electron. If I add for the ion, then it's 3 protons, 4 neutrons, 2 electrons, and nothing because that's disappeared and it's +1. These are different. If you're just talking about the atom, then it's neutral. In a couple of places in your explanation, people called this stable, and that is not true. For a lot of things, it can be or it cannot be. So gold, we find in the ground, neutral, doesn't give up any electrons, perfectly happy that way. You can get it to react with stuff. One of the most famous stories in the chemistry community is the story of the Nobel Prize winners as the Nazis marched through Denmark, I think it was. But if you go all the way over here, all of a sudden they're really unstable in their neutral form. So it depends. And so you don't use that terminology in terms of stability. They are stable once they achieve their ion status. So it's pretty much always safe to say they're stable in this case in terms of their electrons, although they might be highly reactive and want to like bond with something. Okay, we need like 3 more examples. Physical change. You've already answered one. Yep. Dented, sure. Dented. Take something, crush it down. Zane. Sliced. I mentioned, I think, the paper shredder the other day. How we can still piece those back. One more example. Hello, why are you so late?
I just didn't wake up in time.
Excellent. See me after class. I'm going to add one. I didn't see a volunteer, and this is because this one is often overlooked, and that is dissolving. And that is what we're going to talk about next when we talk about things that are aqueous. So if we take NaCl solid, and we put it in water, we get NaCl aqueous. And all that means is that it's dissolved. So if you dissolve something in water, it is a physical change. These ions have separated. Actually, in water, it makes it easier to react, and that's why things in water tend to react more faster. And a lot of our chemistry is water chemistry, because as living creatures, we need our reactions to happen fairly quickly and not with solids. But nothing really has happened. It was Na plus 1 here. And it's still Na plus 1 here, so that is also a physical change. What's not broken or reformed in a physical change? Same again. No atoms are broken or reformed in a chemical change. Or not broken in the way that we would think of an atom being broken. That's nuclear.
There's no electrons.
Yeah. And what are electrons in? They are? Between molecules? What's the magic word for the thing that joins them together? It's James. James? Bond. Thank you. Well done. So you're on the right track there, Zane, because of course it's the electrons in the bond. But we want to be very specific. It's about the bonds that aren't broken or reformed. All the electrons is a little too vague. And we don't get anything new. I'm going to pull out some more examples in a moment after we do some notes once you're doing a little bit of practice. And while we're doing the next one, anybody still need this up? Excellent. Fill in all of these from what you remember last year. What do these symbols mean? Yes. Yeah. Science 10, attendance. Alejandra, Ariel, Ben. Ben's here. Bertie, Felix, Hugo, Jonathan, Kieran, Lisa, Matthew, Naomi, Sahir, Timmy, William K, William R, Zachary, and Zane, and Zoe. Oh, nice. We're getting up there. Okay. Zachary, give me the first three.
Solid, liquid, and gas.
Solid. Do we need to move people back there? Solid, liquid, and gas. And then the last one, Felix. Ask someone. I definitely heard it from someone behind you. Nicely done. Aqueous, A-Q-U. Aqueous means dissolved in water. We do so much water chemistry, we reserve a special symbol for things that are just dissolved in water. We don't do that for any other liquid like ammonia or gasoline or anything else. Aqueous, because a lot of our chemistry occurs in water, so that has a special name. So we have something that's solid, liquid, and aqueous. What is this little thing down here called, the 2? When it's down below and it's kind of lower like that. If you're using a word processor, you're on Google Docs, yep.
Number of like how many elements are?
Oh yeah, it's the number of the elements, but you needed to find it. You're on Google Docs, you're doing your chemistry, you have to make sure everything is subscripted. So that's a subscript. And that is the number of the element. So this means there are 2 A's. And this big one in front, that's actually pointing there. Similar to this one. It's actually similar to math when you put something big in front of it. What's that called? When you multiply the whole compound. Coefficient. So, how many quickly, well, in your time, determine the number of A's and B's in each location. Write them down. So when I call on you, you're like, oh. Do you have a question? I'll call on someone for you. Birdie, how many A's?
Still figuring it out.
Where's, there you are. How, without the 3 in front, if I did this, how many A's would there be? 2. And if you put a 3 in front of it, 6. And just to make it, because some students will go through and they do something different, I want to make sure. What that 3 in front means that there is A2, A2, and A2. And that 4 means that there's B, 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 B. There's 1, 2, 3, 4. So we've answered that one. And then there's 3 of those. So that's 2, 4, 6. So it's always multiply. And you multiply the across the whole thing. So if we were to do the last one here, Ben, number of A's? In this.
Products?
In the products.
6.
6. And the number of B's? Lisa? 4. So that 2 in front means you have A3B2 and then A3B2. So you can see there's 6 and 4. It multiplies the entire thing. So it multiplies across like it's in brackets. If you think about it in math terms, you can think about it like this, and it multiplies in. Chemicals present at the start of a reaction. Hugo. Oh, no. What's the name for the chemicals at the start of the reaction?
Oh, names?
Yeah. And not individually. What is this whole class of things called? The hint is that it's labeled on the diagram.
Oh, reactions.
Excellent. What are the ones that come out?
Products.
Products. Occasionally you'll see the word substrate in reactants if you're doing biology. Same thing. We use the word substrate when we're talking about something that interacts with an enzyme, which is a catalyst for reactions. Anybody still getting things down on this page? Okay. The law of conservation of mass. In a chemical reaction, the number of I used to say just atoms, but then someone said, but I do have the same number of atoms on both sides. And I said, yes, but you have changed some of them. They've become brand new atoms. And that's the part that's not okay. So you have to have the exact same atoms of the same elements on both sides by the time you're done balancing. Matter can neither be created nor destroyed, except in a nuclear reaction, which never ever happens, except it being the largest reaction that occurs in our solar system. Yep.
You're also saying that if you have like dark matter and light matter, the two moves that cancel out.
No, because dark matter and light matter aren't matter and antimatter. So matter and antimatter will cancel out.
Yeah, is that the equivalent to destroy?
When matter and antimatter meet each other, they annihilate each other and turn into pure energy, according to E equals mc squared, which is Einstein's famous equation. So if you have a nuclear reaction and some matter does disappear, it's gone into energy, because there's also the law of conservation of energy, which you'll learn about in physics. Energy can neither be created nor destroyed. And what Einstein, why he got so famous for doing this, is he showed that those two laws are actually the same law. Matter is just a form of energy. And theoretically, energy is a form of matter. You could turn energy into matter, which would take an awful lot. And you can get an awful lot of energy out of matter. Now, we don't have that much antimatter. If you take antimatter as just the electrons are positive and the protons are negative, and if they meet, they completely destroy each other and release a lot of energy. There is none on our planet except for the stuff that we make. And we've been making antimatter for a long time in particle accelerators. We hold it in place with magnets because they have a charge, and so we can just keep them there. And we can even put it in things and give it to people. But if it touches anything, it'll completely react. But the amount we make is incredibly, incredibly small. We can't make very much. So although this law is not quite correct, when you pair it with the law of conservation of energy, they just transform things back and forth to each other. But since we're not doing nuclear reactions, no nuclear, it will always be true, because we're going to focus on the regular balancing. So, from last year, balance this equation. Make sure the number of carbons on both sides is correct. Make sure the number of oxygens on both sides is correct. Just also, I should also check. How many of you have never balanced before? At the very least, don't remember balancing.
Is this balancing?
Balancing, yeah, okay. Before then, I say, oh, go do this thing you've never shown. I'm going to show you a method. And if you, two methods. And one of them isn't really a method. One is the method of, I just look at it until it appears. And then one's an actual systematic method that students have said they found useful. So the first method is it's called the inspection method, where I just take a look at this and I go, okay. I start with the first one. I've got carbon here. I got carbon there. Got one carbon. And I got one carbon. What number is missing by the sides of these? How much there is? How much if they don't say anything? One. So there's always one beside if it doesn't say anything. So I go, oh, carbon's fine. I've got one on each side. Good. Then I go to hydrogen. Hydrogen I have 4, and there I have 2. How do I fix that? Give them both. So I can't like add 2. So one thing you can't do is you can't just make that 4. That would be like crazy sauce. But I'm allowed to multiply. So now there's 4. And now I didn't change carbon. Carbon's still good. Hydrogen's 4. It's fine. Only the number of oxygens have changed. How many oxygens are on this side? 2. How many are on this side? 4. There's 2 oxygens here and 2 there. So I just need to put a 2 in front. Now, this method I'm going to show you is exactly the same, except it's just a way of keeping track, because this is kind of like a balancing act. I have a teeter-totter, and the number of carbons, oxygens, and hydrogens on both sides have to be the same. And so I want to keep track of all those things. So if I think of it like that, then I can be a little systematic about it. I can draw a line, and I can say, I've got, what elements do I have? I have carbon, I have hydrogen, and I have oxygen. And then I write how many I have. So I go, okay, I've got 1 and 1. And I start from the beginning again, so get rid of all my marks. And then I've got 4 and 2. And I've got 2 and 3. And then when I go, okay, carbon's fine. Oh, and yeah, watch out for like oxygen's in more than one place. So that's going to change differently. I'm going to start off. Now, sometimes if I went to oxygen first, I went, how am I going to change this to match? And I've got 3. Leave that till last. It'll often work out. I go hydrogen. Well, that's easy. I can just put 2 here. And I cross that, put 4. And then I have to say, but now there's 4 of these. And then I put 2 there, cross it, it's 4, and now I'm balanced. And this has a double check that I am making sure that I have accounted for every single type of atom on both sides. So if you're having trouble with one, you can do that. Yes, same. Or were you just stretching? Okay. Do these questions. I'm going to go grab some demos that I believe I have on a tray. Where'd my zinc go?
If I take everyone to a beach, they will see like the definition is not. Or like English 20-year-olds go to the beach, they're not like the front row of the school.
Do I have the, what am I doing?
I don't have a kid though. No, they said to come to the bus. Ain't no kids.
In your like shorts and stuff. Okay, write down the chemicals as I use them. And have you predict what I'm going to make. I've got HCl, fairly concentrated, and pure zinc. Zinc metal, again. Now, zinc metal is one of those, it's relatively stable. It will actually slowly react with the oxygen in the atmosphere. But if I add it to a little HCl, make that process go a lot faster, it starts bubbling. What does that tell you about that reaction?
Change in heat.
There's a change. Yeah, there might be. Also, someone took away my matches. What kind of gas is coming off? Who said hydrogen? Excellent. Why do you think hydrogen?
Because it came out of the HCl.
Right. What other gas could it be? There's another gas it could be.
Carbon dioxide?
Carbon is not present there. Matter can neither be created nor destroyed, so you've got the choice of HCl or zinc.
Zinc oxide.
Zinc, metals don't tend to become gases except for really high temperature.
Obviously the Seattle.
Obviously the Cl now. So, that tells us which gas it is. Which gas it is? Which, do you not know the test? That's the hydrogen test. If you light a test tube and it goes chirp, you have hydrogen gas. Is it still going? Yeah, it's still going like gangbusters. Let's have some more. It is quite hot. I'm not going to bring it around for you to touch it. If I held my glove there, it'd probably melt a little bit. It is quite hot. The chirping test is a test for hydrogen gas. How do we know it's not chlorine gas?
Because we're in trouble.
Yeah, you'd get a yellow gas coming off and we'd all be choking to death. Like the first Canadian soldiers. Canadian soldiers have the honor of being the first ones that were subject to gas warfare in World War I. Yeah. Okay. So we get off hydrogen gas. What's a likely product? What's left? We've got Cl, and we've got, and because it's in like this, it's probably Cl minus 1, we got zinc. What would be a reasonable thing to come together with zinc and Cl? Look at the periodic tables. What charge does zinc have, if it has a charge?
No, plus two.
Plus two. We haven't done naming yet. We're going to do this in the future. So if you don't remember your naming, but if this is plus two and that's plus one, how many of each do we need?
2 CL, 1 zinc.
2 Cl, 1 zinc. So the other reasonable thing to do would be this. This is a very specific type of reaction you're going to learn about later called a single replacement. Please balance this now for me. And I'm going to show you another reaction. Which again, all the pieces are supposed to be there and it's not there.
No, then you get rid of oxygen. That applies to both of them. Oh, yeah,
Okay, next one is H2O2, which is where we get the famous joke. A chemist and his apprentice walk into a bar. And ask for a glass of H2O. And his apprentice said, I'd like H2O2. And of course he dies. Because H2O2 is not H2O. There it is. Now, this is a spontaneous reaction. You can tell there's only one reactant in this particular case. We have two types of gases that could be given off. What are the two types of gases that could be given off? Hydrogen and oxygen. Yeah. So both of them could. I just add a little bit of catalyst. So catalyst, this is MnO2, manganese dioxide. It's not taking part in the reaction in that it's not making a product. It's just going to be manganese dioxide the entire time. But it is going to make that reaction go much, much faster. That reaction is happening all the time. It's just incredibly slow at room temperature. Add a catalyst, you can make it go fast. And now, we can see what does that do. Now, we can try lighting it and see which gas that is, and we'll do the test. Is it oxygen gas? Oxygen gas?
No.
No, but what did you notice about the flame? Got bigger.
It's getting brighter.
So do this. Blow it up. Blow. If it's out and it reignites, that's the test for oxygen gas. I don't know if there's any left in there. I just like that so much. Oh, went on, and then and then when I pull it, whoa! Does anybody know what's happening there? Because I put it down, it reignites, and then when I pulled it up, it went out. Why?
It's because at the bottom, the oxygen is heavier
It's not to do with density, although that's a fantastic guess.
Is it because like fire, like uses oxygen to get bigger?
It is, that's why it's reigniting, but why did it go out when I got higher?
Less steam.
Less oxygen.
Pardon?
Because there's less oxygen.
There's less oxygen. When I put it in and I burned up all the oxygen, when I pulled it back up, it was just full of carbon dioxide from the atmosphere. I burned all the oxygen away, so then the flame went out. That's the CO2 test, which is if you put an ignited one and it completely snuffs it out. I don't normally do the CO2 test. That sort of happened naturally in here. Now, a lot of this that's coming out, that's not oxygen gas. There's a lot of water. That's only like 30% hydrogen peroxide, which, by the way, is really quite strong. We normally can't get that in. Well, we can. Regular schools can't. But some of the water is coming off as steam that is generating so much heat. This is also known as rocket fuel, because if you go out into space, you don't have any oxygen to burn. You can't just burn a fuel, so they'll carry hydrogen peroxide and will release oxygen. So if oxygen gas is one of the products, what's the other product? Knowing it can't be hydrogen gas.
Water.
Water. Now notice, I like this example because this does something that a lot of students want to do, which is they take this and they go, oh, it has to look the same. And they'll just like separate it because they just sort of mentally do that. What it is depends on the experiment. It doesn't have to balance here. There's more oxygens here than here, that's why the process of balancing. This Cl was 1 here, then it was 2. You have to fix it with balancing. So fix that with balancing. And so I have another good one to show. See, got rid of that one. Water.
Oh, shit. It's 4 marks? Oh, shit.
Do you use coffee?
Okay, what kind of change is this? Could you put your phone here? Up, watch. It's amazing. Hands up. Chemical. Someone definitely said chemical. There we go. Hands up, physical. Okay, I'm going to give chemical a chance to go first.
Well, I thought it was chemical because like it was just really like 2 chemicals and like they
Yeah.
changed color.
Yeah, it looks a lot like a chemical change. It did change color. What color is this to begin with? And what color is this?
Yeah.
So did anything new happen? No.
I know that was blue. I thought that was black.
Oh, if there's a change and it looks the same as the original, that would actually make it harder to detect a chemical change. This is just food, dye, and water, so that one isn't a chemical change. And in fact, if I take this one and I'm going to add some actual blue, this is copper sulfate. It's a lovely sky blue. Let's get some of this in there. some of it dissolves. Now, chemical or physical change. Has anything changed? No, it was blue before, it's blue now. And what process am I doing? What physical process is going on?
You're agitating.
Dissolving. So I'm just making something that's aqueous. Now, if I add, where's, I thought I had some ammonia here. Oh, there it is. Perfect. Oh, it's concentrated. Oh well. Oh well. Now, if I go like this, before I shake it around, because you get both those colors, is this a chemical or physical change? Why would you say it was chemical? What clues would show that? Something new. Yeah. I'm going to stir it in a moment, but I just love the way it does that at the top. So chemical or physical? Chemical. Why? Something changed. So chemical. So but it just went blue again, right? So sometimes these changes are subtle. They're not as obvious as the changes with hydrogen exploding or something. We can and then HCl. Now, if I add chemical or physical change? Chemical. But wasn't one of the clues that a chemical change is hard to reverse? I just reversed it.
Well, maybe you did this to
You
reverse
didn't
it, you
really
added other verses to
I
it.
did add other things. I changed the pH. This is one of those reactions that is actually, it's an exception. It's incredibly easy to reverse. It goes both ways. If I add ammonia, it'll go to one side and give us one product. If I add HCl, it'll go to the other side and do another product. It depends on whether I add an acid or base. So it's acid-base sensitive in terms of reactions. We tell you that they're difficult to reverse because we're thinking about things like fire. If you burn your diary, no one's ever going to be able to read it in the history of the universe. Whereas if you shred it, someone could theoretically piece it together. But some reactions are actually incredibly easy to reverse. So all of these are clues. They're not in and of themselves perfect. They don't instantly mean it's one way or the other. You just have to add them up and then take your best guess. What do I have? AgNO3. Oh, I need more count. I need more testers. One more, I think, or two more. Nope, wait, all good. So let's go with AgNO3. AgNO3. And NaCl, we would be fine. Okay, no, NaCl. Where's, oh, there it is. Oh! It's in a beaker. Actually, this would be a good one to predict. While I'm doing this, with your knowledge from last year, predict the products. That's AG, not a J, G. And behold, chemical or physical change. Wow, I've given it away there. What kind of change is that? I don't know. And essentially, there's a whole little series of magic tricks you can do as a chemist, where you turn water into wine, and you turn it into milk, and it's just all of these. Don't drink it ever. If a magician does that for you, because they're like things like silver. This is how, if you've taken traditional photography and you have to develop film, this is one of the solutions you make that comes out, and you can see it's chunky. If it's milk, it's really bad milk.
It's like really liquid.
Yeah, it's pretty bad. By the way, if you ever have milk that's gone bad, like it's just been sealed in the container, it's gone all chunky, because it's pasteurized, the milk that you buy in the store, even if it is chunky, it is completely safe to eat. It might make you throw up. Thank you. Excellent staring. Well done. But the fermentation process that happened to make it go chunky is itself not going to actually do anything to you, which is why companies like Dairyland or Island Farms use that to make all their chocolate ice cream. So if the store gets like a huge batch of like cream cheese or milk and it just goes bad in the store, like it's gone a bit rotten, they just send it back. And then it's no milk solids. They just process it, throw some chocolate into it, and put it in the big tubs of chocolate ice cream, and then it makes ice cream. Yeah. It's recycling. Don't have a lot of that one. No. Pardon? That's CL. Okay, your predictions. What are one of the products? What are one of the products? AGCL. Oh. Which makes sense. You took the one that was in front here and matched it with the one that was second there. NaNO3.
I got it between Na2.
And cleverly, you didn't break that up. If you remember from last year, that's a polyatomic ion. It stays the same. This is a double replacement. This is a decomposition. This is a single replacement. All the types we're going to do later. You don't have to worry if you don't understand that now. But now we've got a balance. What number goes where in here? Yeah, here.
2 in the first molecule.
2 here. And that's it. We got H2 and Cl2. 2 there makes H2 and Cl2. We're good. Anybody have a balancing for this one? Yep.
2H2O2 and O2 plus 2H2O.
With 3 oxygens, you needed to make it even so that you could make 4, because you can only go 2, 4, like 6, 8. So by making that one 2, make that 2, it makes it 4. Now we've got 4 there. Perfect. This one, the most difficult of them all. Yes.
That one's good, just weird.
That one's good just the way it is. We didn't do anything fancy with that one in particular. All of those are doing well. Yes, they are. Everybody done with these questions up here? Excellent. No complaints. Then see here. Maybe you should.
So serious, go to the
Last one is the
no.
I think up front one would be good. And then if that doesn't work, maybe over there.
Yeah, maybe to the
Although you did it again. How do you? Is there like oil and water or something? What have you done? Why did I say you did it again?
oh segregated.
Yeah, you segregated yourself again. Yeah. All the female identified houses are there. And then clearly all the male identified houses are here, except for one table that just took over there, but they're all in one spot, so it sort of goes like
but
this.
also it's sort of happened and then the seating. That's how they just.
Yeah, which everybody here chose.
But yeah, I know, but there's
Yeah.
something like this.
Yeah, but you know, I haven't been checking. Someone could have moved, I wouldn't have noticed. Yeah. Zane, first one.
Yeah. First one?
Yeah, what do we see here? You're moving up. Quick, go.
The law of conservation of
Yeah. Chemical reactions. Matthew.
Use substances.
There we go. See here without telling. Although, see here, you have this question, number 3. Yeah. Which of the following is not a true statement concerning what happens in all chemical reactions? To make it easier to identify, I'll do this. Which one of those is wrong? C. Excellent. You don't get new atoms. All atoms are the same. There's a statistical analysis that sometimes we do with chemistry students later on. Just to show you the sheer number of atoms, it is statistically certain that you are breathing a molecule of air that was also once in the lungs of Julius Caesar. Absolute statistical certainty. Because there's so many molecules in that volume that when that goes out and mixes, it's going to eventually go everywhere and it's going to be dispersed in the environment. You are probably breathing in one right now, the way it's dispersed. And I always think that that's phrased in a very particular way. First of all, they chose someone famous. They chose someone famous that in a particular culture. And you could choose it another way. It is with a statistical certainty that you are breathing in a molecule that was once inside someone who farted. And you could pick anybody that's famous from history, and you could also say exactly the same thing. It's all true. When you eat things, there's a statistical certainty that some of those molecules once were in the body of someone else, because of course it would have decomposed, gone into the atmosphere as CO2, and now you're breathing that in and out. These molecules are mixed and mixed and mixed and mixed all over. And they are not new. Atoms are old. Unless we make them in the sun or a particle accelerator. Last one. Ariel. Louder? Chemical equations describe chemical reactions. Yeah. They're not only biological, they don't give directions, and they don't show how to write chemical formulas. So that's the best one. We did that one. And time is it? Yeah.
let's do these ones then. Let's get right into balancing. This is a method that you can use, and they're just again a series of hints on how to balance. There is, if you're keen on math, the algebraic method of solving balancing equations. Most of the time, it's like trying to hit a fly with a nuclear bomb. You're going to get it, but it's going to take you a lot of time and energy, and a lot of paper is going to be wasted. So we're going to do this one. Later on, if you really want to, I will show you how to do the other method, and it will balance any equation no matter how hard it is. Trial and error can work. It's very inefficient, and so these clues can help. These clues are: balance compounds first and elements last. Only balance one thing at a time. If you were trying to balance two things at a time, you're going to get caught in an endless loop. And you are only allowed to change coefficients. Very occasionally, I will get someone doing this. And they just do something like, and they erase it. I'm like, you can't do that. You can't change what it is. You can only change how many. And hydrogen and oxygen are really annoying. Someone's phone is ringing?
I think that's what it's super.
Maybe. If they appear in more than one place, like they did in our H2O2, not that particular example, because they're the only ones there, actually. That's a terrible example. If you were looking at one, they appear in more than one place, balance them last. They'll often just work out. And if they're both there, pick the simplest one first. Polyatomic ions, like sulfate, and you did that very well when we saw AgNO3, you kept the NO3 together, can be balanced as a whole group. So when you see AgNO3, and let's make it a little bit more complicated. Let's go with MgNO3 2 plus NaCl goes to MgCl2 plus NaNO3. What the NO3 is doesn't matter because it's on both sides. So if we were to write down what we're balancing, we would go, oh, there's Mg, there's NO3, there's Na, and there's Cl. And then you could go through the process that way. You can treat this just like a blob. You have two blobs on this side, one blob on that side, so you need to have two there. You have two Cls there, so you're also going to need two there, and then you're done. So treat them as whole things. And then when you're done, double check. Now, a lot of these rules, I go through it quick because until you do the problems, you're not going to have that much with it. Try these next one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hands up, yes.
If it's like a polyatomic ion.
Yes, that's exactly what it is. Polyatomic ion.
Yeah, like if you see this blob, does it not even matter like what's in it?
No, you just NO3 is NO3, and you treat it like one thing.
But if you're trying to, if there's, okay, actually no.
I will show you what I think you're reaching for.
Yeah.
And that is, there is, in this type of equation, it's a blob. But if you have this type of equation, sorry, BaO plus now you can't treat it as a blob because sure, it's NO3 there, but it's NO2 here. Something weird has happened. And now you just have to balance it without that. Yeah. Because they can break down. And if it's a breakdown question, then no. See here? Practicing balancing. Okay? What's with the banging? Okay, now take the cart back. Oh! There's one demo I forgot. Sorry, it's the most amazing demo. Chemical or physical change. Copper wire. Haven't even done anything. Okay, watch. Can't believe I forgot. Sir.
Do you have to fill in each book?
Each spot?
Yeah.
Nope. This is a good question. If you leave that blank, what number is it? 1. So if you leave it blank, it's automatically a 1, not a 0. That's the only thing.
Do you want us to write a one?
You do not have to, but if you do, especially in grade 10, I won't mark you wrong. If you're doing it in grade 11, I'd probably like, you don't have to do that anymore. But you're allowed to, especially in grade 10. Because sometimes it's nice just to fix it in your mind. There's 1. So
Is that 19? Why? You said I knew it.
You have 12 carbons, 12 carbons,
So much you
then
can
you have
do it.
28 hydrogens, so you have 28 hydrogens here. But this makes 24 oxygens plus 14 oxygens. That makes 38, so that's 19 O2.
this is probably also a good time to mention your balancing quiz on Saturday.
What?
Hold on. Damn. Damn, man. You want a piece of
It'll be quick. 5 to 10 questions.
I did.
Who said Mr. Rowan?
I have a question. So for this one, is it just a
I got a massive.
You got a massive one?
Yeah, it's 1902.
Ooh, clever.
But it makes sense.
Huh?
1, 2, 3, 4, 5, 6, 7, 8,
Makes sense.
13, 14, 15, 18. Ooh. So 9 groups of work. No. Oh no, I don't have enough. Okay. Everybody done? Everybody not done? Keep going. Keep going. I'll give you another couple minutes.
Is your first live or?
Oh no, no, all of them. All the way up to number 10. See here? Stop distracting. He moved up. You told him to move up, and now you're distracting him. Yeah, don't do that. Yeah, yeah, yeah.
Oh.
According to your sources. You are correct.
This one too? This tiny one?
Oh no, not that one. I'm going to show that one in the future.
Okay. In order to quickly, very quickly, check your answers, your group number is the same as the question you have to do. So question 1 is done by group 1. Do it on the board and show your answer.
Yo.
Find a spot, put the number next to it. There's whiteboard pens over there.
Okay, what do you got? Wait, what's the free? Damn, bro.
I'm near the board.
You don't have to put down all the dashes. You just write a balance.
Yeah, that's cool. 3.
Wait, Hugo, is this correct?
Wait.
Can you help me?
Let me go.
Oh, no, you don't have to. Is that correct?
Oh, yeah, it's fine.
Okay.
You got the master number one? 1902. Yo, we got the easy one. Yeah, okay.
The one that we were told.
Okay, Timmy, Naomi, where are you? What numbers are you putting up? 2.
And then like there's nothing on that one. And
Yeah.
then
Okay. Kieran and Hugo.
We just did 2 on like the HCL.
Okay. Felix and Zane.
That.
What? Read it out to me.
1,
14.
3, 2. Wait, can we just choose?
Lisa and Alejandra.
Which group number are you on?
Yeah, just read me out the numbers.
Oh, and then nothing.
Nothing. 5. Ariel and William. What'd you get for this one?
2, 19, 12, and 14.
19, 12, and 14. We might come back to that one. 6. Zachary and Matthew. 2, 4, 2, 4. We're going to come back to that one. 7. William and...
1, 2, 1, 2.
Shh. We're going to come back to it. 7. William and Zoe. What is it? 1, 2, 2, 1. 8. Birdie and Ben.
We're still working on it.
Okay. 9. Jonathan and Sahir. 3, 4. Are you done?
More. We run everything in product.
Are you still working on it? Hugo, are you helping them or something?
Yeah.
Don't help. Just let them work. Let them work.
You need to say all these gaps. So if you got all these gaps, you need to say each number in this gap. Okay, so here's
3, 4, 12.
3, 4, 12. Looking good. And then Mr. Neufeld will do the last one because it's the most famous one. There we go. Okay, return to your seats. I got 30 seconds to show you one thing. Oh, Birdie and Ben, do you got it?
No.
Keep doing it on your paper. I will ask for it for you next day. Oh, I will discuss it next day. Next day is our demo day.